All right, in section 2.3, we're going to start looking at some more algebraic and kind of formal ways to talk about infinite limits. So these are essentially limits that are going to be either positive infinity or negative infinity, either from the left or the right, or for the whole limit. So in general, we're going to look for when x approaches some value and gets arbitrarily close from either side, does the f of x value, does the y value kind of go up or down unbounded? So if we look at it with a table, this first one we see x approaches 1 of 1 over x minus 1. So if I fill out this table, I'll get negative 10, I'll get negative 100, I'll get negative 1,000, undefined at 1, but that doesn't matter for a limit, remember. We have 1,000 on this side, we have 100 on this side, we have 10, and then we have 4. So if I look at the limit coming from the right, so if I look at the limit coming from the right of this function, so the right would be numbers bigger than it, always bigger, so that would be x is going this way, and in this case what you see is the y values kind of keep getting bigger and bigger and bigger. I know it's not 1,000 because if you look at the jump from this one to this one, it's quite a jump. In a normal limit, when it's going to a real number, it's a very, very, very small difference between that value and that value. But this is a big number, and if I get even closer to 1, it would be even a bigger value. So these appear to be going higher and higher unbounded. So we would say this is positive infinity. But if I look at the limit from the left, just like before, that has to go to the same place. But if you look at this way, as we go from the left, numbers smaller than that value from both sides, then I would get negative infinity. Now, since 1 is going to positive infinity and 1 is going to negative infinity, this limit would not exist. Now, if they were both positive infinity or both negative infinity, then sure, we could say the limit exists, but in this case, different places does not exist. Now, if I look at the next one, you can see it's pretty much the same problem, except for the number on top is different. It's negative 2. So what's going to happen when I fill out this table? If I put in the 0.9, I'm going to get 20 and 200 and 2,000 and undefined and negative 2,000 and negative 200, negative 20 and negative 8. So you can see basically all the signs have changed, and really that's just because I'm changing and multiplying these big huge values by a negative number. So in this case, as I go from the right, seems like it's going to negative infinity. And as I go from the left, it seems to be going to positive infinity. So this limit also does not exist. So really what we're looking for is if it's going to the same unbounded value from both sides. Right-hand limit exists, left-hand limit exists, of course, but the limit itself in this case does not exist. So this is kind of what we're looking for when we think about infinite limits. We're looking for limits whose value is positive or negative infinity. Okay? So if we want kind of a formal definition, we can say if we have the limit as x approaches a of f of x, if this equals infinity, this basically means we can make f of x as large as we want, as x gets close to a from both sides. So as we can make the y value, the f of x value, we can make it as big as we want as we get really, really, really close to a from both sides. Now, we're never going to touch it, but we're going to get very, very, very close. And the same thing if I wanted to talk about the limit as a negative infinity value. If we want to say negative infinity, then we would just say basically we can make f of x as small. And when I say as small, remember a really, really big negative number is really, really, really small. So it equals negative infinity, we can make it as small as we want, as x gets close to a. Now we're going to kind of use some logical thinking in this case. And the way we're going to do that is we're going to use something that's called maybe the little big principle. So if we think about this, if I take a number, let's just take some number, let's take k. K is some number. Well, if I divide this by a small number, some super small number, something smaller than k, then it is going to get bigger. So if I take a real number and divide it by an infinitely small number, it's going to be an infinitely big number. Think about an example. If I take 2 divided by 0.01, then I would get 200. But if I take 2 divided by 0.001, I'll get 2,000. If I take 2 divided by 0.0001, I'll get 20,000. So the smaller number you divide by, the bigger your quotient is going to be. This is kind of this concept of you're dividing by smaller and smaller numbers, so that's kind of the concept of a limit. As we get closer and closer and closer to 0, these values get larger and larger and larger. Now, of course, we can look at the graph and see how that works, and we've seen infinite limits that way, but trying to think about them algebraically can sometimes be helpful. -1. So let's look at some examples, and then we'll also kind of look at the graph to see how these work. So these all talk about the limit. The first 3 talk about the limit from the right, the left, and then the total limit. So these are going to be, the first one says the limit of 3 over x minus 2 as x approaches 2 from the right. Well, remember, from the right, these are numbers slightly bigger than 2. So if I take a number slightly bigger than 2 and I subtract 2 from it, I am going to get a very, very, very small number. So this is going to be 3 over a very super small number. And I can make it as small as I want. If I pick it to be 2.000000001 and then I subtract 2 from it, then I can get 0.000001. Well, if I take positive 3 over a super small number, that's going to be a super big number, which we can think of as positive infinity. Because I can make the bottom as small as I want, that makes the top as big as I want. Now, same thing for from the left. Now, from the left, these are going to be smaller than 2. Now, if I take a number slightly smaller than 2, let's say 1.9999999, and I subtract 2 from it, I'm going to get 3 divided by a super small number, but that super small number is going to be negative. So if I take 3 divided by the smallest number negative ever in existence, that is going to be negative infinity. And now for the limit, that's really simple now that you have the left-hand and right-hand limits, because this would just not exist because the right-hand and left-hand limits go to different spots. Now if I take a sketch of this graph, the interesting thing is happening obviously at 2, and you can go ahead and graph this in Desmos or whatever. I'm just going to make a quick sketch of it. So I see it looks something like this. So one side goes like this, and one side goes like this. So as I approach 2 from the right, so x is slightly bigger, so this is approaching from the right, and you can see the graph does go up to infinity. And as I approach from the left, the graph is definitely kind of diving down to negative infinity, and they go to different spots from the left and right, so of course the limit itself will not exist. So graphing is always a great way to go, but just kind of thinking it out, but even before I even looked at the graph, I kind of had an idea of what this would look like. Okay, let's go ahead and look at this one. So this one is 1 over x minus 1 squared. So slightly different, but let's do the same logic. So this is going to be slightly larger than 1, so maybe 1.000001. So when I subtract it, 1.000001 minus 1 is something really small. So I'm thinking 1 over a super small number squared. Now a super small number squared is actually even smaller as long as it's less than 1. So this is going to be positive infinity. But this was a small positive squared, still positive infinity. Now the left hand is a little different in this case because this is going to be smaller, 0.99999, something just to the left of 1. But when I subtract it, I'm going to get 1 over a negative small number. But when I square a negative small number, it becomes positive. So this is also positive infinity. Because whenever you square a negative, it becomes positive. So the negative in the bottom with the small goes away. And now these both go to the same spot, so the limit is just infinity. Now if I sketch this one, you'll see that this definitely agrees. So the interesting thing here is at 1. So if I graph it, this graph looks something like this. This one kind of goes up really high. This one does the same. So you can see that both of them, as you get arbitrarily close to the value of 1 here, is going to infinity. Both sides go to infinity, so we would say it is infinity. So now we just have a couple others. So this one we have x approaches -3 of -1 over x plus 3. So if I don't want to use the graph, what I could simply do is I could just do both sides limit again. So -3 from the right, and the limit is x approaches -3 from the left of -1 over x plus 3, -1 over x plus 3. So from the right, remember, is going to be slightly bigger. And this is going to be slightly smaller. So slightly bigger than -3. So if I think of -3, some numbers bigger than that would be -2.99, and some numbers smaller would be -3.001. So if I take the numbers bigger, I'll -1 over something that is slightly positive, because -2.99999 plus 3 is going to be a really small positive number. Well, that's going to be negative infinity. And the reason is I have -1 divided by a really small number, which is going to give me negative infinity because of the negative sign on top. Same thing for the bottom one. A smaller number would be like -3.0001. So that's going to give me -1 over a really, really small negative number. That's going to be positive infinity because you have two negatives, a -1 on the top and a really, really, really small negative number on the bottom. These go to different spots, so this does not exist. Now this is an interesting one. So in this case, I have x's on top and bottom. So whenever I have x's on top and bottom, that's a pretty good clue that it might not be an infinite limit. But if I plug in 2, what I'll actually get is I will get 0 over 0. So this problem is actually not even an infinite limit because 0 over 0 is indeterminate. So in this case, this is one of those that we have to factor. So x minus 4, x minus 2, x minus 2, x plus 2. Those cancel. In this case, I can just plug in 2 in. 2 minus 4 is -2. 2 plus 2 is 4, so this limit is -1/2. Now, the question is, why did I put this in here? Well, the reason I did is not all limits are infinite. So I know we're doing infinite limits in this section, but you got to remember, it's always good to plug a number in and make sure that you don't get 0 over 0. Typically, you'll get infinite limits when you plug in and you get 1 over 0 or something over 0. That's generally when you're going to get an infinite limit. But again, if you look at the graph of this at 2, there is no infinite limit. Now, if I were to do this at -2, this problem actually does have an infinite limit at -2. But in this case, at 2, just a regular old limit. Now, we can also do some of the special trig functions and find their infinite limits. Now, these are pretty tricky. You have to kind of use some of our trig values. So if I want to do the limit of 3 pi over 2 from the right of secant, what I'm going to do is I'm going to write it as a fraction, as 1 over cosine theta. Now, cosine of 3 pi over 2 is 0, so essentially I'm getting 1 over 0. So what I want to know is I want to know what's a value slightly bigger than 3 pi over 2. So if I think of 3 pi over 2, 3 pi over 2 is here on my unit circle. So some values bigger than 3 pi over 2 would be kind of things in quadrant 4. Those are bigger than 3 pi over 2. So if I think of the cosine value here, the cosine value over here, cosine is the x value. So cosine value in this quadrant is going to be positive. So essentially this is going to be 1 over a really, really small number, which should be positive infinity. Now these, quite honestly, are pretty tricky to do with just the algebra. Most people, quite honestly, will probably just look at the graph. And if I do graph this, what you'll see is there's an asymptote at pi over 2 and 3 pi over 2. And you can go ahead and graph this. And so we have a value at 1 and negative 1. So these go something like this. So as I go from 3 pi over 2 from the right, well, here are values from the right of it. So as I approach from the right, what you can see is this part of the graph is going to positive infinity. So indeed, this graph does go to positive infinity. All right. So again, graph is going to be a good way to go for a lot of these. As you can see, they pretty much will tell you what they are, but always nice to kind of use the algebra and get the concept. If it is a regular number, a real number divided by a really, really small number, that will be infinitely large. Okay, let's look at this last one. This last one is a mess. We have sine x, which oscillates over x minus 2. We want to know what happens as it approaches 2. So I'm just going to look at the graph of this one, because this one is pretty bad. And 2 is not a real nice number for sine, but if you look at 2, essentially this graph has an asymptote here. And this graph looks something like this. It's actually kind of a cool graph. I suggest you graph it. It kind of looks something like this on this side. And over here it's kind of oscillating. It kind of goes down something like this. It doesn't really matter what's happening because I just want to know what happens from the left because we're going from the left. So from the left you can see that these f of x, these y values essentially are going down. So the limit from the left is negative infinity. Now if I wanted to do, say, just the limit as x approaches regular 2 of this function, well in this case it would be does not exist. Because from the right you can see it's going up forever, but from the left it's going down forever. So they're going to different spots, so that would be a does not exist limit. So a little bit of algebra to help us with our infinite limits, but of course the graph and the tables and things like that are obviously going to be really beneficial as we move through this section.